Thanks. So I present some joint work with Giannicola Scorpa that we mostly did while we were in the CWI in Amsterdam. So, okay, so Entangled games. So we already heard about Entangled games, but just like, a brief reminder and, just to get used to some new pictures. So we have Alice and Bob. They receive some input X and Y according to some probability distribution. They output some A and L, and they want to satisfy some function V. And so they can share an entangled state, and they're not allowed to communicate. And what we want to know is the maximum probability, that the best strategy for Alice and Bob to actually win that game. And so one natural question here is, and one natural but complicated question is about parallel repetition, right? So instead of having one game, they play n games in parallel, meaning that Alice has, n inputs x1 to xn, Bob has n inputs y1 to yn, and each pair xi, yi is taken according to this probability distribution p, and they want to output, n times a1, an, b1, b1, and they want to win all of the n games at the same time. Right? And the question is, what is the best strategy to do so, right? And so, of course, they could play each game independently, and if they do, they would win with this probability omega star g to the power of n. Right? And the question is, can they do better? And so there are some examples when you can do better, but most generally the question is, what can we say about this quantity omega star of g to the n? So, okay, so the standard view is that we look at these games and we want to know what is the maximum probability that they win this game. But right now, let's talk about, let's do a little step on the side. Instead of being interested in the probability that Alice and Bob can win the game, we'll be interested in the minimum amount of resources that, of additional resources that we give to Alice and Bob, such that they can win the game with probability 1. So, okay, so that's a very general statement. So, okay, so what kind of extra resources? So extra on top of this, this shared entangled state. So, for example, you could allow them to communicate. Or another thing, more generally, you could allow them to, such that this state, the state they share depends on xy, right? So we're interested in this, we'll be interested in this second question, but in the end, since I'm talking about parallel repetition, is how answering this question help us understand this first question, the probability that they can win those games. So, okay, so, and our approach here is that we'll consider states that depend on their input xy. So the state they share here, phi, instead of being independent of xy, can have some dependency. We'll see what kind of dependency it can have on xy. And we'll show that this approach will actually help us to answer the parallel repetition question. And okay, and our results, okay, so I'll directly say what we're going to show is that for any game G on the uniform distribution, meaning that the questions of Alice and Bob are independent and taken from a uniform distribution, if the value of the game, of one repetition of the game is 1 minus epsilon, then the value of the n-fold parallel repetition is bounded by above by 1 minus epsilon squared to the power of omega n divided by some parameters that depend on the game, on the size of the game. And so these things are pretty standard, except that here there's also there's log k plus log L. So recall that k is the dimension of the input space, L is the dimension of the output space. Yeah. So.
Sorry. In the classical case, there's this odd cycle game, which you can easily see. It's simple to see why there is no decrease in the probability for two games with respect to one. Either a simple example in the quantum case, which is illuminating.
Okay, so there are. Okay, some people will know this better than me. I think okay, if one has a simple answer.
Yeah, there's this Fortnow-Feiger-Lovász game. Has value 2/3 for one repetition and two, even in the no signaling case.
Yeah. So yeah. So even in the entangled case, yeah. So it works for two, but as n grows, this thing will decrease exponentially.
And the completeness is classical. Like it's.
Yes, you can achieve 2/3 with a classical deterministic
These are uniform distribution.
Sorry?
None of these games are uniform distributions.
Yeah. So I'll not talk about this, but if you're just interested in some kind of exponential decay, actually you can have some pretty weak, such a weak theorem for general distribution, because somehow you can pad, you can plug any general distribution into a uniform distribution of greater size. I mean, you can play with this thing. So if you're only interested in something which is exponentially small, then actually these kind of theorems go to general distributions. But like here you'll have, so instead of log k, you would have k, and actually, I mean, you have some other weird parameters that depend on this property distribution, which can make it grow very large. But so yeah, and so okay, and so here, so all of this is pretty standard, except from this input size k, which hasn't appeared. So so it's not a problem, for example, if the input size is equal to the output size. So for example, in these cases, then the log k plus log l will kind of be the same. But in some cases, it can worsen a lot the parallel repetition theorem. So it all depends on your applications. Okay, so let's go back to this picture. We said, okay, we're looking at Alice and Bob. They have a game, and they have a state that can depend on x and y, and they want to win the game with probability 1. Well, okay, so if we don't add any restriction, if we just say it like this, then, I mean, it's not really interesting, right? Because, for example, in this state, Alice could have full information about y. Alice could know y, Bob could know x. And here, they can trivially win the game here. So it's a little bit too easy. So we want to add them, to give them the extra resources, but somehow we want to limit the joint dependency in xy of this family of states that they share. And so one of the main parts of the talk is to define a little bit what is this joint dependency, what is the quantity that will be interesting for us. Okay, so quantifying the extra resources. So, okay, so we start from a game. Okay, so we fix a game on the uniform distribution, and we assume, let's say, that the entangled value is smaller than 1. Now we give to Alice and Bob some these extra state phi xy. So this means that Alice and Bob share this state. So this is the input they receive, the output they receive. So they get each xy of probability 1 over k squared, and then they have this state that they share. Right? And we assume that with these states, Alice and Bob can win the game with probability 1. And okay, so what we'll define as the extra resources, we'll be interested in the quantity, so in the amount of information that these states give to Alice and Bob about each other's inputs. So, and more particularly, we'll be interested in this quantity. So what is this quantity? It's the mutual information between x, so x is Alice's input, and by. By is everything that Bob has. So this quantity here corresponds to the information that Bob has about Alice's input x. And also here, conversely, this is the information that Alice has about Bob's input y. So assuming that Alice and Bob share these states, phi xy. Okay? So this is the quantity we'll be interested in. And now I'm going to define the information cost for entangled games, so on the uniform distribution. So what we want to say, we're interested in this quantity IC of G, which is the minimal amount of information that these states have to give to Alice and Bob about each other's input to win the game with probability 1. And so more formally, we have considered the states that Alice and Bob share, and we're interested in the minimum amount of information that these states that Alice and Bob have about each other's input when sharing this state row. Right? And somehow this is some kind of analog to the information cost notion used in communication complexity, right? So I mean, for those who know, you have this communication complexity task. Instead of looking at the communication between Alice and Bob, you're just interested in the minimal amount of information that they have to that they have to know about each other's input to solve this communication complexity problem. So somehow you can see this as an analog. So we have this well-defined notion which involved this information, and it's kind of it's parallel. It's related to this information cost, which was really useful in communication complexity. So we're happy, and we have. So we think we have a nice notion to work with, and and we should be happy. But actually, we're not very happy. So first, I'll show you that this information cost doesn't do really what we want. So, and so let's just try to toy a little bit with this quantity. Okay, so start from a game, a CHSH game. Okay, so we know what is the CHSH game. We know that the value of the CHSH game is cos squared pi over 8. And now we'll give to Alice and Bob these extra advice states. So so on input xy, so if it's 0, 1, so if they have input 0, 0, 0, 1, or 1, 0. Okay, so this should be 0, 1, or 1, 0. They have 1 over root 2, 0, 0, plus 1, 1. And if they both have input 1, 1, they should get 0, 1, plus 1, 0. Right? And you can easily see that if they share these states, they can win the game with probability 1. Right? So they share this state. Alice will just measure her register in the computational basis. Bob will measure his register in the computational basis. And and if they get 1, 1, then they'll get different outcomes, and if they get any of the 3 other inputs, they'll get the same outcomes, right? So when they share these states, they can win the CHSH game with probability 1. But on the other hand, you can see that if you look at these mutual information, and if they share this state, actually this doesn't give any information about the other player's input. So I mean, you can calculate the reduced density matrices, or you can just see that for example, if Bob has y equals 0, then Alice will have a totally mixed state here on her input, and also a totally mixed state on the shared state. And it will be the same thing if y equals 1. So so somehow it felt that it was a good notion that the amount of information that you give away about each other input, you felt that it was a good notion, but it doesn't capture exactly very well the extra resources, right? Because even though this information this sum of mutual information is 0, there was some extra, there are some extra resources. Yes?
So have you considered conditioning on A and conditioning on B? So in your mutual information expression?
So
if you condition on A for the first term and condition on B for the second term?
it would still be 0. I mean, usually what you would do is that you would want to know, actually, usually what you would do is the opposite, is that here you would condition on Y. You would like to know the extra information given by the state given, apart from their input. But here, the distribution is uniform. So they would, anyway, they have no information. And here, if you condition on A, it will also be 0. And here, there's no... So yeah, the normal information cost, you have to remove what you know a priori about the other player's input. But here, since it's all uniform, it's all 0. So... So that wouldn't change, but it's the state of mind, right? I mean, we have to change something in these, in this quantity to make the thing work. So, and so what we will do is actually something a little bit weird. So we have the same setting, we have we have these shared states, but now what we want to know the amount of information that Alice and Bob know about each other's input. Instead of just looking at what happens in this here, we'll kind of consider a purification of this state. And so somehow we'll have, so we'll say that, so we'll copy this, for each Alice and Bob, we'll copy these input registers, and we'll consider a large purification, a superposition of the inputs, the advice state, so the input of Alice and Bob, as well as the advice state phi xy. And we'll consider this notion of mutual information, which is here. So it's pretty much the same. So on the one side of this mutual information, you have x. So you have 2 copies of x, but since you trace out x bar, so this is still classical x on the left side. But on the right side, now when we consider Bob, we don't consider Bob like in the usual setting, but we consider Bob, which has a superposition of his inputs now. So somehow, this quantity corresponds to the information that Bob has about Alice's input x, but he is now, we add the thing, we allow him to be somehow in a superposition of his inputs y, right?
What do you mean by superposition? I just see the input twice.
Yeah, but Yeah, but it's also quantum.
Yes.
So,
But it's something he could just generate himself with a C0, right? So
if,
how can it
okay,
change
so
anything?
what is true is that the fact that it appears twice is not an issue. The only reason why it's twice is to actually be able to trace out a part and to separate the classical and the quantum part.
Okay, so what
But
changed?
he cannot go from here to here.
Ah, okay, yeah.
right?
Now I see the
So
difference.
I agree that here there is only one Y, it wouldn't change anything, but this is still more powerful than this.
Yeah, yeah, yeah.
You could have just had one X and one Y, but then instead of that being sub omega down there, it would have to be, for the first one, you pretend that X has been measured. And the second
Exactly, yeah. So yes, so it's actually how it's defined in the paper,
Okay.
but this is more compact, right? And it's also how, and this also relates to the quantities which are defined in the next paper, because they also use actually the same quantity, so it's just for uniformity. But yes, definitely, and if you do it like this, there's no something very deep here in like having two copies of X and Y. It's just for, so that there is this compact kind of formula. Okay, yeah, so here similarly is the information that Alice has about Y when she's in the superposition of her X's, right? Okay, and now so we define this superposed information cost, which is the minimal, so it's the minimal amount of information that is kind of superposed information that is leaked by these states, such that Alice and Bob can win with this state with probability 1. So this new quantity, okay, so it's not clear. It's not clear why we define it like this. Later, there will be some kind of motivation why this kind of definition works better than the other one. But okay, first thing, let's check whether this definition still has the problem that we have with the CHSH game, right? So because this notion of IC was not very good, let's see if superposed information cost does better. So okay, so again we fix the same advice states here. Again, you replace 0, 1 by 1, 0, and okay. So now when you're interested in the amount of information that Alice and Bob have about each other's input, we said okay, we look at this big superposition. And the quantity we consider is this thing. And now what's going on? If Alice has X equals 0, then, okay, so the advice state will be, no matter what is Y, the advice state will be 0, 0 plus 1, 1. And, so for both 0, 0 and 1, 1. So Bob will have, you trace out the A part, and Bob will have this state. If X equals 1, what happens? So if Y equals 0, the advice state is 0, 0 plus 1, 1. But if Y equals 1, 1, then the advice state becomes 0, 1 plus 1, 0. So here you can see that, if you just look at the Y bar register, you can see that if Alice has X equals 0, Bob will have 0, 0 plus 1, 1 in this register. But if X equals 1, here Bob will have, half 0, 0 and half 1, 1. So Bob will now have a mixed state. So here Bob will have a mixed state on Y bar, and here Bob has a pure state on Y bar. So somehow, now with this definition, Bob has some information about this Alice's input X. So, okay, we don't know if this definition is good, but we know that it's not as bad as the other one. We know that at least, for the CHSH game, when we take this weird, this weird sum of mutual information, we get something that looks better, right? And so this problem does not occur. And is this a good quantity? And yes, right. So what are the properties of the superposed information cost? You can actually relate this very nicely to the value of an entangled game. So you can show that actually the superposed information cost of the game is larger than epsilon over 32, right? And like this is one of the main ingredients of the proof. And okay, so there's two things. First of all, this wouldn't hold for the normal information cost because we said that the information cost of the CHSH game is 0. While its value is not 1. So typically this is, the reason why we have this superposed kind of definition is to be able to do this kind of inequalities. Also, a second thing, it's also hard to have a nice notion of superposed information cost for general games when you don't have the restriction of the input distribution. And, it's not clear, like, typically you would want to look at this conditional mutual information but it doesn't follow that easily to find a nice quantity in information theory that relates to the value of an entangled game if you don't have this restriction to uniform distribution, or it would probably work for free games as well, but for general games it's it's pretty hard. Okay, so second of all, additivity, right? So this okay, so this is a larger equal. So additivity is that the sec of gn is equal to n times sec of g. So that's because it's mutual information, right? I mean, we just apply a chain rule. These are things that we have pretty easily, right? So somehow, because we work with mutual information, these things work pretty well. And third of all, that's, looking at this mutual information, then the third step would be like to bring it back and to relate it to this value of omega star g of n. And so it appears that we can show, okay, here there is like, there's like a disclaimer, so it's not exactly what we show, but something in this spirit, we can show that this value sec of gn can be upper bounded by something which depends only in this parameter t and not in n. Right? The important thing is that the thing is independent in n, right? And just by plugging these inequalities, we get the result directly. So then then the result just follows, right? Okay, so what I'm trying to show you is to convince you that this works, which is really, showing this means that this, that this notion of superposed information cost, is useful. Is useful when studying the value of entangled games, right? So, okay, so
question. Can you go back to that slide? So, do you have inequality in the same direction of your upper bound on sec gn, but only for one copy of the game? In other words, can you upper bound?
Okay, no. So the answer is that this works only because gn has a specific, because it's a tensor product of n different games.
Okay.
You can have some counter examples here where what can happen is that if you have a game which is with half probability, I have a trivial game with which I win with probability 1, and with half probability, a game for which this superposed information cost would be very large, then if you take like with half probability trivial and with half probability hard game, this new game has omega star g which is equal to half, but the superposed information cost is still very large. So you can't go, you could put something on the other way, but it would depend on the dimension, so it would be probably, it would be very, very weak. Yeah. So here it works, yes, this works specifically because we're working with GN. Yeah.
You mentioned that you don't exactly use the superimposed information cost, but what you do use, is the thing you do use also additive, or do you need to...
Yeah. So basically, the thing we use, this will also, all of this will also hold to epsilons and to some other mess. But yes, so it's exactly these inequalities, but this means that basically there's a lot of errors and epsilons and things going on, but...
Is it sort of additive because you round it back to the superimposed information cost, which is exactly...
The thing is that the other thing we use, it will also be with mutual, there's also be a chain rule that will work.
Okay.
For,
So the log k that appears in the bound, is it because your bound is not tight, or because this quantity cannot be better than upper bound?
We don't know that this is tight, so it's probably not tight. In the next talk there will be, in the next talk they also use some similar quantities and they don't have this log k, but it appears it's not so similar after all. So it's not clear, okay. So sorry.
We also have a notion like this, but then for classical games.
Okay, so that's okay. So when
because the CPU uses this purification trick.
Yeah, so basically this will not work in the classical case because there's no Ullmann's theorem in the classical case. But just to see that so actually the problem that we have, is this the problem? This already appears in the classical case. So here, the advice state, if you just say that you have an advice probability distribution, you also, so let's say that the classical way of defining IC would also be bad. So you would have to classically superpose Bob, whatever that means. It's, I mean, it's an interesting question, and it's not clear, what to do, whether there's a good quantity. You would need to superpose such that there is a classical Ullmann theorem, and So actually, in the 5 minutes that I have left, I'll try to show you where do we use this superposed, where the superposed quantity appears in the proof, right? So I'm going to give you a little bit of insight about this proposition. And okay, so recall that this doesn't hold for IC. And actually, I'll just show you, like a weaker statement is that if the superposed information cost of a game is 0, then its entangled value is 1, right? Which is already, and then you don't, then it's a small leap of faith to know that, if it worked for 0, then it works for epsilon. Right? That's okay. So what does it mean? So fix a game G, the superposed information cost equals 0, meaning that there exists a family of states of this form, such that two things. Alice and Bob can win with probability 1 when sharing these states, and if they share this other state with these superposed inputs, this doesn't give away any information about each other's inputs. So that's just the definition. And okay, so and the mutual information is positive. So if this is equal to 0, it means that each of the parts is 0, right? Okay, so and now what will we do? So we'll first show this lemma, which means that means that Alice, there is a unitary, so for all x, there is a unitary from Alice that can remove the dependency in x of, well, let's say for extra copy, that's easy, but more interestingly, in the state phi xy. So somehow, there is a local unitary on Alice's side that transforms any phi xy to phi 0y. Okay, so that's so that's the first lemma, and how do we prove this? So they start from this state. And, Bob has no information about, superposed Bob has no information about x. So we'll define psi x to be everything apart from this, the first x in register x. And what does it mean that Bob has no information about x? It means that if you trace out Alice's part of the state psi x, well, it's the same for all x. That's, that exactly means that Bob has no information about x. There's no way, So it's this, right? And once you have this property, then you can apply Ullmann theorem. So this is just an application of Ullmann theorem, meaning that if this holds, then locally Alice can transform psi x into psi 0, right? And then you can see that, okay, so psi x is a little bit larger and includes the yy, but then you can see that the only way that this can work is if for all y, this thing holds. So, and here is where, and for all of this, for all of this reasoning to hold, you really need to assume that Bob's input is in some kind of superposition. Ullmann theorem doesn't work like with mixed states, something, you must have like some kind of pure state, apply Ullmann theorem, and do something. So if you would want to apply the same thing in the classical case, you would have to invent like another model, which is stronger than the classical model, so that Bob could have some extra information around here that will allow Ullmann theorem for probability distributions. Right? So, and the interesting thing to think, actually, I haven't developed the thing, but but so just to see that here, really, this superposed notion is really important. And once we have this, then we basically have it all. So Alice can remove her dependencies in x. Symmetrically, Bob can remove the dependency in y by applying a unitary Vy. Yeah. So here what we showed is that basically they can go from phi xy, and if they each apply ux and vy, they can go to phi 0, 0. So now if we want to, if we want to construct a strategy for a game, then we'll just do the opposite. They start with phi 0, 0, which is independent. They apply ux dagger and vy dagger, and they obtain phi xy. And by definition, we said that if they have phi xy, they can win the game with probability 1. So, so we conclude that the value of the entangled game is 1. So, yeah. So, okay. So, just to recap, so this works. This as I said, is the chain rule on mutual information. And this is what I'm not going to talk about because a little bit, but exactly. Yeah, but so I did talk about it. You have an intuition. I mean, if you're interested, we can talk about it. It's not very long, and if you want to see where this input size comes in, and yeah, and so the standard conclusion. Thanks. Yeah.
Does the superimposed information cost reflect the communication cost of creating?
Yes. Okay. Okay. So that's something.
I mean, I guess you've shown one special case of that.
Yeah. So okay. So that's an interesting thing to have, right? So you have a x and y. So you have some box which is so between two players, and they have some amount of communication, right? So let's say they can share some state phi or whatever. They have some communication T. And what you can say is that, okay, at the end, let's say they have some, they do everything unitarily, whatever, they have a state phi xy. So if you look at the classical thing, okay, then so if you were just looking at the information cost, it would be pretty easy to say that the information cost is a lower bound on the communication complexity. Right? Because I mean, if you look at the mutual information, it cannot be more than the than the amount of communication if at the beginning there's no information between x and y. And you can also do the exact same kind of reasoning for the superposed information cost by saying the following. Okay, so this is like a black box. We know that for each xy there is a procedure that does this, and now instead of plugging these classical inputs, Alice starts from sum over x, and let's say Bob has a classical y, and uses this x as a control.
Oh, I believe that, but the hard part is achievability, right? You don't like achieving.
Oh, achievability. Oh no. Okay, no, we don't know. I mean, sorry, but it was just to say that how that if you start from a black box and you start from a superposition, then you have the superposition. No, achievability. Sorry, yeah, that's an idea.
If there are no more questions, let's have it again.